Miles is going to give his proposal, tell us what he has been doing in the past almost 4 years. And I witnessed Owen's growing period during these four years, and he's approaching academic maturity gradually. And today is the exciting day, and he's going to tell us. The title is here: Multiple Particles, Nonlinear Dynamics in Spatial Temporal Periodic Potential. And the format of today's thesis proposal is he is going to give a presentation and postpone your questions at the end of his talk, and then we will have question and answer session. And after that, the committee member will stay and discuss his proposal. Okay, Owen.
You hit the lights for me. So I'll go through in a relatively chronological order, sort of how the question that I want to be working on developed. And so this multiple particles dynamics and this special time-dependent potential is the body of the talk, but we'll get there in the following way. So we'll start with a particular device and some of our experimental findings and why that led to a numerical investigation. And then we'll talk about what we mean when we say spatiotemporally periodic. And we won't say those words anymore because there's too many syllables, so we'll just say STP. And then the current methods of understanding them, as well as, and then we'll move on to the work on multiple particles and in this very simple model to discuss some of the fundamentals. And then I'll give a proposal on what I want to spend the rest of my time figuring. So, starting with this device, what is this device? It's a series of electrodes embedded in some surface, and depending on the waveform of the driving potential you apply to them and the geometry of the electrodes and the phase separation between adjacent electrodes, you can get different fields above the surface. So here we work with the simplest case called a two-phase electric current, where adjacent electrodes are 180 degrees out of phase, and so at some time the field looks like this, and then as time increases it oscillates, flips, and then comes back. And as far as where this is used, where you would find something like this, well, cleaning dust. Any good story starts with cleaning, maybe? I don't know. But this one certainly does. So our original funding came from NASA working to clean highly charged particles that you would find in extraterrestrial environments off of solar panels. And some of the other things this device has been used for is controlling blood cells in some aqueous solution, and in general particle manipulation and control, which can be used from everything from distributing toner and printers to maybe distributing nanoparticles on a surface to change the refractive index, and separation and liquid drop control as well. So without further ado, we worked on cleaning first, and that's what we did. We successfully was able to mitigate dust. We showed that, unsurprisingly, if you increase the driving frequency, you get better clearing efficiencies. So it's a little hard to read, but this is for 20 hertz, and this is for 80 hertz, and the time it takes is much smaller. And then we wanted to understand what was going on so we could develop better control or mitigation applications. And we found a variety of qualitatively different behaviors, like simple oscillations following the field lines, relatively random particle trajectories, some trajectories that stabilized in weird potato shapes, orbits above the surface. And so to simplify the problem so we could attack it from a simpler perspective, we reduce the dimensionality. And so we will discuss a couple of experiments we did with this setup. Another option would be constraining motion to the surface. But in this particular setup, we use a linear quadrupole trap to confine particle motions to one dimension. And then on either side of the trap, we have an electric curtain where, again, adjacent electrodes on one side are 180 degrees out of phase, and opposing electrodes are in phase, so that the component of the electric field perpendicular to the axis of the quadrupole is 0, and the component along the axis of the quadrupole has this periodic nature to it. So what does this actually look like? We have a laser illuminating a couple particles in the quadrupole trap being operated on with this device. And for small values of, for small electric fields, here this plot is the position and velocity, so this phase plane as, and we've shown it for several different values of field strength driving. And we find for small values of driving, we have a small limit cycle or periodic orbit in this phase plane. And this grows as you increase the driving amplitude, and you reach a certain point where the motion qualitatively changes. So instead of oscillations about one set of electrodes, suddenly you have oscillations happening between two sets of electrodes, and then eventually three. So without going into a lot of detail, we see a couple of interesting features. And then for different set of initial conditions, or if you increase the driving, you can get these propagating trajectories. So making these devices is tough, and controlling them is tough, and so we wanted to investigate different areas of the parameter space, different setups. Quickly, and one of the ways to do that is to take a numerical approach. So for our numerical approach, we need some expression for the potential above the surface, so we can find equations of motion. And the potential on an electrode repeats itself after every two. So these two electrodes have the same potential applied to them, and this repeats itself across, let's approximate as an infinite array of electrodes, and we can solve for the potential by wrapping the y greater than 0 plane into this circle. This is your sort of basic electrostatics problem, and solving for the electric potential of just two electrodes, and then unfolding your answer back out into the physical system of interest. So we work in a quasi-static regime, meaning relatively low driving frequencies, so we don't have to worry about any induced magnetic field. And the potential we find looks like this for some value of time. And as time increases, black goes to white goes to black. And the equations of motion we've expressed here in a first-order autonomous form. And what do I mean when I say that? I've removed the explicit time dependence that shows up with this trivial equation, and that increases the dimension of the phase space. The reason I'm showing this is because this is important when considering the types of bifurcations that we'll discuss that occur in this system. So x1 is the position, x2 is the velocity, x3 is the time. We have dimensionless position. Y is just a number, or where you're setting your one-dimensional axis to be, so that's either the location of the axis of the quadrupole or your surface. Beta is some dimensionless damping. And here we've shown an example of a trajectory that's either random or in transient behavior. Position, velocity, time. Time is periodic, so we just wrap the trajectory back up from the bottom. And we get these spaghetti-like tendrils, and this is fine for one particle. So This can also be represented as a toroid, and I want you to keep this image in your mind when we talk about Poincaré sections. The position, which is periodic, we've represented as an angle, and the time, which is periodic, we have as some other periodic axis. So if we consider some array of initial conditions, and all of these points are functions of time, and we map them forward by some amount of time with time map. If we choose that time map to be the period of the driving, we get a Poincaré section. And why is that? Well, we've essentially just chosen a slice of the phase space. That's one less dimension of the full phase space, and we plot points as a trajectory passes through it. And that's known as a Poincaré section as long as the trajectory passes through in a transverse way. Because of the relentless increase of time that we know and deal with in our daily lives, the time maps are a good way to have a guaranteed Poincaré section. So if we project our final state into the position axis and do this for many values of A, and generate a histogram, we get bifurcation diagrams, and we can see a variety of different behaviors. We show for several different values of the damping. For small damping, the picture is so complicated you could spend years analyzing the different types of transitions occurring. So we work with a larger value of damping where the picture is a little simpler. If we choose some value of A, where it looks like something interesting is happening, some smear of blue and a couple of different lines passing over it, and we unfold what's actually happening and look at it. So we choose A equals 0.3. These are the initial conditions color-coded based off of where they'll end up. So if we map forward in time, 2, 3, 4, 8, 21, we end up in this final state where we have 2 point attractors, called attractors because initial conditions in their general vicinity have mapped through them, so they're asymptotically stable. And then something else happening here. And if we watch this move forward in time, not by maps, but by smaller amounts of time, we would see that these are propagating trajectories, this one traveling in the positive x direction and this one traveling in the negative x direction. So these are important trajectories, even in the multiple particle case, which is why I'm showing them. What happens if we look at this? Well, it turns out if you zoom in even further, you can see self-similarity. This is a strange attractor or a chaotic attractor. When you have a feature like this, you want to find how fast initial conditions diverge from each other, and we can calculate that number. But moving right along, what do we find in the 2D case where particles can hop off the surface? This is getting more towards this complicated multiple particle interaction picture. And there's really only one feature I want to spend any time on in this case. And that's what I call the force field feature. And that's something that NASA would care about. So what is this? Let's start on the left side first. We have 2 attractors in the horizontal plane and one in the vertical, or 2 attractors, projected onto the position axis and one on the horizontal axis and one in the vertical axis. And these correspond to stable oscillations above 2 electrodes where a particle attempts to follow the field lines as they oscillate. On the right side, we've increased damping, and I'm sorry, I should have said that we've switched to varying damping just because we find more interesting features. I won't spend any time talking about the increase of A in this situation. But for large values of damping, the time average force dominates and points in the directions of the antinodes of the potential where your force is 0. And this is similar to the Birkin's force in acoustics, and particles end up oscillating above each electrode. The 2 lines here tell us that it's a period 2 oscillation. And so the question is, what's happening in between? Well, in between, there's essentially a competition between these 2 ideas, and it turns out there's almost no stability in the horizontal direction. So if you drop particles onto the surface, and your system is configured in this state, then they'll simply oscillate above the surface, and if there's some DC component, some airflow or some added DC component to the phase of the electrodes, then particles will just move away without ever even touching the surface. So there's a bifurcation sequence happening here. This is relatively unphysical. This is a one-dimensional bifurcation sequence happening right above one of the electrodes for very specific values of damping, so we won't talk about that. But so now that I've shown you the system in some of our previous work, what does this have anything to do with this type of potential that's periodic in space and time? And what do we mean by that? Well, we mean that our device makes a potential that oscillates in time periodically and is clearly periodic in space. And we're really looking at sort of commensurate spatial and time values. So, and we'll talk about how you simplify these systems. So, if you can express your function, if you can express your potential as some function of the spatial coordinate and the time coordinate or parameter, and this is periodic in space and this is periodic in time, that's what we mean by spatiotemporally periodic. That's not very surprising. So where do these pop up? Well, the kicked rotor is a simple example where you have a delta function time dependence. Josephson junctions, you end up with a similar relationship that's found in Kapitza's pendulum, which we'll talk about in a minute, where your spatial coordinate is the phase between either two superconductors or superfluid states. And also in transport control and ratchets and controlling other potentials by adding in some high frequency time dependence. So a specific example that's relatively famous, Kapitza was most well known for his work pioneering superfluid helium, and he also created this sort of toy problem, which is now known as Kapitza's pendulum, where if you oscillate the suspension point of a pendulum, you can stabilize the inverted state. And so in the equations of motion, we find some periodic spatial component multiplied by some periodic time component. And the way to understand these is the sort of the most obvious thing to do that we always do is express the potential as a harmonic oscillator potential. Look for small values of x. And when we do this, if we leave the form of the time dependence as a general time dependence, this is known as the Hill equation, and this has been around forever. He published his paper on this, looking at celestial body motions in 1886. So, but an even simpler case that's even more well known and is a specific case of the Hill equation is the Mathieu equation. This is the canonical form of the Mathieu equation, where basically what you've done is chosen the simplest first order time dependence, say cosine of t. And the solutions to the Mathieu equation are well known: cosine elliptic and sine elliptic functions. And without going into any mathematical detail, what these are, we can pictorially discuss them for just a second. In the limit of q going to 0, clearly we just return the sine and cosine functions. This is the q axis. Here's time. There's different orders of the cosine and sine elliptic functions, and clearly they have a variety of behavior. But perhaps their most important aspect is the stable and unstable regimes. So by unstable, I mean that the solutions run off to infinity. By stable, I mean they stay localized around some spatial value. And this stability map of the parameter space is shown for 3 different values of damping. And you can see, unsurprisingly, that as you increase the damping, the area of the stable region increases. and this is how mass spectrometers are built. You design and tune a system near one of these boundaries where masses of particles of one mass fall in the unstable regime and particles of another mass fall in the stable regime. And if you push them through the system, which could be something like a quadrupole trap, you'll get the ones out that exist in the stable regime, and the other ones will fly off. So these are used all over the place, and there's one other way of handling them, which is perhaps the most important way. Landau and Lifshitz have a brief chapter on their book, brief mention in their book, and Kapitza used this averaging method. So a lot of people use averaging when you have some time dependence in your Hamiltonian or your equations of motion. And Krylov and Bogolyubov, correct me if I'm saying their names wrong, they just generalized these, how do you say it? Yeah.
Krylov is right.
I say what?
Bogolyubov.
Oh, okay. Can I just point at you and have you say Man,
We were commenting how serious they look.
Oh yeah. That's how I feel. No. So they generalized the method of averaging. They didn't come up with it, but they generalized it in a nice form. And actually, there's a great paper that I think is necessary to point out because these people found an effective Louisville equation for a classically. Thank you. For a classically driven system. Man, I'm gonna botch every name. I'm happy there's no one here correcting me on the French names because there's a few of those too. And they use this Hamiltonian-like formalism to describe the flow of possibilities in phase space, but they don't include particle interactions. So now on to our work. At the more fundamental level, we will talk briefly about a single particle in this very simple potential, because the types of bifurcations that occur are important when you include multiple particles as well. So we've chosen our potential shown here. We have a dimensionless oscillation amplitude, dimensionless space and time. We've shown for one period and just wrapped all the dynamics into this one period. And this bifurcation diagram was made in the same way as before. We do include dissipation, and we just set a value to beta equals 0.6 because some interesting features are very clear. And what happens when you choose different values or different values of time, different Poincaré sections within the toroid, the types of bifurcations don't change, and so you end up with this very nice movie, but it doesn't change any of the important features of the system. And so this movie is generated essentially by taking your bifurcation diagram, but slicing your toroid at different places and showing that sweep. So let's talk specifically about the first two bifurcations, and without any detail whatsoever, I'm going to talk about flow case stability multipliers. Did I get that one right? Okay. We use the symbol lambda because that's what's traditionally used for the flow case stability multipliers, even though we've already used this for the wavelength of our potential as well. So just keep those separated in your mind. And how these stability multipliers act in the complex plane, because they're complex numbers, is a way of classifying bifurcations. So, so the first two bifurcations that occur projected onto the position and velocity phase plane are shown here. And we see what appears as a point bifurcating into what appears as a limit cycle, and then some clear shift happening at some other point. So this is just different values of our oscillation amplitude. the same sort of the same dependence as the bifurcation diagram. And a Hopf bifurcation is when two of the stability multipliers cross the imaginary axis, traveling from the negative real to the positive real, part of the complex plane. And we've shown here the real and imaginary parts of the two stability multipliers. It's not exactly easy to figure out what's happening, so it's best to watch a movie. But why isn't this first point bifurcating into a limit cycle of a Hopf bifurcation? And if you're familiar with bifurcations, this is generally how a Hopf bifurcation is defined. So why is it not? Well, I told you what a Hopf bifurcation diagram was as far as the stability multipliers are concerned. What do? Well, first of all, they cross in the wrong direction. And then one of them runs off past the unit circle along the real axis. So they cross the imaginary axis here at around 0.53. And that's nowhere to be found on this diagram. So this is happening at around between 0.7 and 0.75, which in our plots over here, -1, the real part is right there. So clearly the bifurcation happens when it crosses the unit circle. And that's not surprising. That's a well-known type of bifurcation, but it's a critical flip bifurcation, a period doubling bifurcation. And so why is this a period doubling bifurcation? Well, that comes back to the explicit time dependence of the equations of motion. In the equations of motion, excuse me, what appears to be a fixed point is actually a limit cycle. And if you didn't have this explicit time dependence in the equations of motion, then you might have a Hopf bifurcation or something else. But the point is it's there and it needs to be considered. And when you consider it, this first trajectory is just along the time axis of our toroid and isn't moving in the position of velocity phase plane. And then it picks up an extra period, so it goes from a period 1 to a period 2 limit cycle. So the next bifurcation, what's happening here, again we see some interesting features in these plots, but it's easiest to watch a movie, thank goodness. We see some motion and then one of them runs across the unit circle in the positive direction along the real axis. And this is known as a cyclic fold bifurcation, where one side of the trajectory picks up some preference and one lobe enlarges, and there's two possibilities when this happens, the right lobe enlarging or the left lobe enlarging, and here only one of the possibilities is shown. And this is known to cause hysteresis in systems. This is another important type of bifurcation. So why does that matter for the heart of what I'm talking about, which is what we finally arrived to? Multiple particles interacting in one of these types of potentials. Or now, because we have more than one particle, we can't just wrap all the dynamics into one period of the potential unless or if we do, we need to consider specifically what concentrations we're looking at. And we call the concentration the number of particles divided by the number of periods over which we're looking at the system. And depending on the number of the relationship of these two values, you can have different dynamics. So we need to calculate the force on any given particle in this system. We consider it a simple Coulomb particle interaction. And to do this, we need to be careful because the long-range particle interactions in a periodic boundary condition is we can't just consider nearest neighbor interactions. So we're working in one dimension. We can calculate the force if we know the distance. This is the simplest case. What's just the distance between two particles, and it's not a stretch to say that the next order of the calculation of the force will be considering an image, an exact replica of this on either side. and the force contribution of this particle and its image on the left and the image on the right will be 0 because these are both the same distance away. But these other, the other particle's image will be non-zero. And it turns out that if you sum up the forces in this way, it has this very nice representation in terms of polygamma functions. And why is that useful? Well, they're known to arbitrary precision, and we've essentially, and really it simplifies the sum, because instead of having to cut off at some order, we can consider all orders and just perform the sum once to find the forces. So this is unique to the one-dimensional case. So let's show some results, pick some parameters, and throw up some data. We choose a unit charge interaction because it's going to be similar to the values of the oscillation amplitudes that we're looking at. We choose a unit mass. We leave beta as 0.6, and for now, just look at what happens in one period for different numbers of particles. So some pretty pictures, but let's count some things. N equals 2. The number of apparent attractors before the first bifurcation is 1, plus the one that's hard to see, which is at the seam of the boundary. That's 2. When n equals 3, we have 6. 5 here, 1 at the boundary. N equals 4, it's back to 4. N equals 5, it's 10. So for n odd, there's double the number of possible attractors. So let me say just a couple of details of how these diagrams were made. For each value of A in one sweep, and for 10 different sweeps, we have random initial conditions that settle in to some final state before being projected onto the position axis and plotted all together. So keep in mind that this is a variety of possibilities all overlap to generate this colorful bifurcation diagram, which is really a histogram of possibilities. So we show the periodic position as an angle, and for small a, we know that the particles will be attracted to an antinode, and that's similar again to the Birkin's force in acoustics. And the other two particles, at least in the even case, oscillate in such a way so that their net force on the particles at the antinodes is 0. So these particles are not moving, and these are oscillating. When n equals 3, let's say, we have one particle that settles that into an antinode, and the other two essentially compete over the remaining one. But again, they oscillate in a way that the net force on the particle at the antinode is 0. So clearly you have two different possibilities when n is odd, which is giving you the doubled number of attractors in the odd case. And that's fine and good, but something interesting happens when you move from n equals 6 to n equals 8. So here we've shown the value with which the first bifurcation occurs, and we've split up the even particles and the odd particles. The even particles are shown in red, and the odd particles are shown in blue, and clearly something changes from 6 to 8. So a bifurcation diagram of one run, one sweep of A is shown for n equals 8, and it looks a little different. So how do we understand that? Well, without being too specific, we see that when n equals 6, this extra attractor is, this is hard to see, but it starts here, and it's squashing the first bifurcation that's happening. When n equals 8, this first bifurcation sequence doesn't exist at all. So what is this attractor that's sort of smushing out the first bifurcation sequence? That's an attempted propagating motion. So like in the single particle case, we had these propagating attractors in the phase plane. In the multiple particle case, you have a transition where you suddenly jump into, or you can jump into a case where the particles are trying to travel in a direction, but there's no net transport because it's one dimension and it's essentially a standing wave field. And so they are colliding with each other, and I say that word loosely because they have some long-range interaction. So that's a very loose description of what's happening. So we want to come up with some way of finding that transition without having to watch specific particle dynamics and without having to do a Fouquet analysis on multiple particle trajectories, which is just a beast of a problem, or at least a pain. And so, looking at trying to understand this, we actually we turn to statistical physics. So specifically, we look at the variance of the kinetic energy squared, and we assume nothing about the velocity distributions in this calculation, so it looks something like this. We scale it by the average kinetic energy squared to give us the squared fractional deviation. And these plots look interesting, but I want you to focus on one specific feature, which is the discontinuity that exists in the squared fractional deviation. And this discontinuity corresponds directly to this attempted propagating motion that happens after whatever series of bifurcations that occur. So in n=6, it clearly took up a lot of the bifurcation diagram we showed, and so it does here as well. And one of the motivations for calculating this is that in real systems, you don't have access to all of the information to make some bifurcation diagram. We can watch these movies and see that the trend, when goes from 6 to 8, the first bifurcation stops being some explosion of, I won't say period doubling because it's not clear if these are really periodic at all, but it's when n is greater than 6 even, it's clearly a cyclic fold bifurcation where the symmetry of the trajectory shifts and changes. You end up with the two possibilities that are shown here, but no period doubling occurs. So we can't use loose words like propagating trajectories without defining how to discover when they occur in some real way. So another thing you can do is look at the velocity distributions. And actually, I didn't include a slide on that, but I have one to show if you're interested. And really, the motivation for calculating that quantity came when looking at non-integer concentrations where the situation is drastically more complicated. So not only is this a non-integer concentration, but we've reduced the value of the interparticle potential, and there's this clear qualitative change that happens here, and that qualitative change pops up in this quantity right here, as shown here. And it's not surprising, qualitatively this looks like some clustering transition, and the squared fractional deviation of the kinetic energy is used in the study of granular materials to look for changes in the effective numbers of degrees of freedom. So we pick up this qualitative change with this quantity. And that leads me into my proposal. So what do I want to do with the rest of my time here? Well, it turns out you find something really interesting if you look at the squared fractional deviation only in the Poincaré sections. So we've called it E prime because we choose the Poincaré section where the value of time for which the field potential is 0. And it turns out that as you change A, this value, there's a clear increase and then a decrease as you further increase A. So an increase in the effective numbers of degrees of freedom and a decrease. And so these numbers are small. It's important to remember that we're doing this in a perfect model where we're just starting with random initial conditions. So fluctuations, which is another thing the squared fractional deviation measures, fluctuations are only occurring from small differences in your initial possibilities. If you have some real system where natural perturbations are present, or you have some external source of noise, then this peak would be violently larger. We've also plotted it with the bifurcation diagram, and clearly this number is largest in between whatever transition is happening here. So another version of this peak is shown for n equals 3. So what I want to do is understand the statistics in the Poincaré sections, because Poincaré sections are traditionally used as a way of simplifying just an observation of the trajectories in a phase space. A strange attractor that would look like garbage if you just projected it onto one of the phase planes. If you take a Poincaré section, you can clearly see the structure that exists. It's a way of seeing things that aren't, that wouldn't be easy to see, but maintaining the essential, the most basic nature of the system. So my question is, what are the differences? What information can we gain, and is there anything important that can be gained out of looking at the statistics in the Poincaré section? So we need to look at some things like maybe density or velocity correlations, comparing them to Poincaré sections versus the actual system, maybe include some natural source of perturbations or fluctuations. This isn't entirely from the hip. We have a nice paper by Anatoly Polkovnikov and his student. He was actually here only a couple years ago, Polkovnikov was, and they published this nice paper on many-body energy localizations, transitions in periodically driven systems, where they use the Magnus expansion to find an effective Hamiltonian for Kapitza's pendulum, actually, and compare this to a quantum version of the system. But the Magnus expansion is a powerful tool, and one that could potentially give us an analytical understanding of what's happening. And the reason the Magnus expansion is because it qualitatively maintains properties of the system through any period of its or for any order of the calculation. So you need to prove things like, that it doesn't diverge, and these are things I'm working on now with Anand, and he's helping me understand some of these tools. So that's what I would like to continue investigating along. I'd like to acknowledge Dr. Wu and Jeff, my advisors, for really teaching me everything, and as well as Chris Danforth and Anand for putting up with my incessant badgering and pushing me in the right direction. Thanks to the VACC for their computational resources, and thanks to NASA for putting food in my mouth for a little while. And thanks to the whole physics department for my education and your support.
So now is the question and answer session. Any questions?
I have a question. So it's related to the introduction, but somehow, perhaps towards the end, it's related also to the end. And I only understood the introduction a little bit. I don't know much about the Hopf bifurcations and so on. So what is the relationship? So you talked about the Kapitza pendulum, which is the case where you have very strong oscillations, right? For very large frequency, you can imagine that you have inversion of the pendulum equilibrium, right? Mm-hmm. Whereas the other aspect that you mentioned in the introduction, the Mathieu equation, has to do with stability near fixed frequencies, right? You have a driving force at frequency 2, in your units, or half integers of that, or something like that, right? And then you can have, trajectories that become unstable, which is parametric resonance, right? So there is no relationship between those two, is there? I missed a little bit. And then in the final, in the final thing, you mentioned Polkovnikov's paper, and you mentioned again mapping of the Kapitza pendulum. So in other
Yeah,
words,
yeah.
and the reason I'm asking is I want to learn because we are covering this in classical mechanics tomorrow.
Yeah,
So,
yeah.
and last time. So in my mind, the first problem,
Yeah.
the Kapitza pendulum,
Yeah.
like you average over the fast. I mean, you find an effective
Yeah.
potential for
So-
the slow modes.
So let me talk
Right.
about that in a
Whereas
little
the
more
second
detail.
one,
Yeah,
is not, right?
there's two. So that's why I mentioned this averaging method and not the averaging method. Is essentially what you're doing in the averaging method is you're considering some fast driving frequencies. So your small parameter is the period, and you're separating the equations of motion into the slow and fast parts, right?
right?
So that's how you come up with an effective potential that gives you this inverted stability, right? So this other approach, the Mathieu equation approach, is different in that you're actually looking quantitatively at the small oscillations about that point.
But the frequencies are not large there. The driving force frequencies are integers.
Yeah.
Like they're 2 or 1.
So there's different
your
ways. Yeah,
right?
there's different ways. Right. I think what you're talking about is the characteristic exponent of the Mathieu equation.
No, the stuff under the cosine, right? Under
Yeah.
the cosine you had like 2t.
Oh, 2t.
You know,
Yeah.
you have, the instability, the parametric resonance instability occurs
Yeah.
for very specific frequencies
Yeah.
that are not necessarily large.
That are not necessarily large.
Is
Right.
that right?
That's absolutely right.
Okay.
Yeah. Yeah. Did I answer your question? I'm not sure.
No, I guess I was answering what is the relationship, what is
Yeah.
the relationship between two phenomena and which
Yeah,
one
yeah.
did you say that you observed in
Okay.
your studies? I was confused.
Yeah. So we're looking mostly at this ultra nonlinear case where. And we have considered the more linear case and essentially what you just come up with the Mathieu equation, right? Or you can attack it from a different perspective, which is to come up and separate the fast and slow parts of the motion. And there you're throwing out the fast parts of the motion, which is what you're finding with the Mathieu equation, as far as my understanding, in that approximation of fast driving frequency. Is that, you'll agree with that?
Let me say a few words. In Kapitza's example, in Mathieu's equation, they are for single particles, and one is for potential, which is spatially periodic and temporal periodic for Kapitza's case. For Mathieu's equation, only temporal periodic. There's no spatial part. So these are two simple examples, but Owen is looking at much more complicated.
Right.
Both spatial and periodic. Also, the particles more than one, and they are interacting with each other.
Right.
And that was the thesis main.
Oh, right, I understand. But also in addition, the part that I mentioned is the simplest part at the very
Yeah.
beginning, which is, isn't it
Yeah.
true that in the Kapitza case, it's the Mathieu equation with very large frequency, that's what I'm saying, right? In order to have inversion
Yes,
of
absolutely.
something, you have to have driving
100%
frequency
right.
to be the largest parameter in
Correct.
the problem. Not 2,
Yeah. Yeah.
1, but it has to be the largest
That's
one.
the
right?
only way you
And
can
that's not what you
linearize.
do,
Yeah,
right? You do
Yeah.
fixed frequencies and you have parametric instability. right?
absolutely, yeah.
So, right, so it's closer to the Floquet analysis of the Mathieu equation rather than to the Kapitza case. That's the part I didn't understand. The analogy with the Kapitza pendulum is that you have very strong, very fast oscillations,
Mhm.
and then the ground state gets inverted. Correct me if I'm wrong.
Yeah, that's right.
Yeah.
Yeah. I think
So you don't do that, right?
We don't.
No.
We consider so small a, small dimensionless driving amplitude, is large driving frequency. When you non-dimensionalize
Right.
your equations of motion, maybe this is getting more to the heart of your question. A is proportional to 1 over omega
All right, so maybe I
squared.
understood it
Yeah.
right. Yeah, because you have in the cosine you have 2, which is a fixed number,
Yeah,
and then A is related to the internal frequency. Right?
yeah, yeah. So
So when A
A,
is small,
mhm,
the ratio of the driving, which is 2, to the
Driving is
internal, which
large.
A, becomes large.
yeah,
Okay.
driving is large when A is small.
Okay,
Yeah,
now I
I
understand.
should have maybe explicitly mentioned that. Yeah.
Any other questions?
I might as well continue. So what is the... so when you talk about the instability, the only thing I understand is instability of the Mathieu equation, which is just that the amplitude, it becomes, there is a Lyapunov exponent, e to the positive number times t. So in those graphs for many particles and so on, it's the same It's
So
the same kind of
That's
instability.
well. That's exactly
It
the
grows.
question now. Is how so? How do you come up with an effective description when you have particle interactions?
Right.
And that so half of the problem is defining the problem, which is exactly how are you going to consider your particle interactions? What's going to be your small parameter? Because if you put them, for instance, let's say you have one Kapitza pendulum and you just stuff on a bunch more Kapitza pendulums and they're all interacting, you can't linearize in the spatial coordinate because the particles want to move away from each other. And so that's what we're dealing with now is how to, and that's why I pointed out the two papers that existed. One which came up with this what I didn't say was some compressible flow in this in the phase space as a form of a solution, and they loosely said that this was related to many-body, even though there's no particle interactions. And then this other case where Volkovnikov used the Magnus expansion on a quantum system interacting with these discrete jumps in the potential. Anyway, so maybe I can talk to you in more detail about this later, but that's a great question.
But roughly speaking, you have many charged as Kapitza pendulum, I guess, right?
Yeah, so
To interact with long-range force.
yeah.
I like a very subtle Vim acknowledgement.
Oh yeah.
The general question for you is, how is that related to you cleaning the surface?
Yeah, great question. So the reason the electric current works for cleaning is if you just have really fast driving in the electric current, then particles don't move. And if you have really slow driving, then they move too slowly to move off the surface. So the electric current only operates in the regime where the spatial periodicity and time periodicity are similar, is one way of putting it. So it's a very nonlinear system where you have not only multiple particles interacting, but the only way to levitate them and move them in the system is through these nonlinear trajectories, which is essentially what we're saying.
If I can, so in all those plots, this A is always small, is it right? So you always have a fast driving frequency?
Relatively small.
Yeah.
Yeah. So again, it's not, because this isn't analytical work, we're not restricted to some specific regime of A, and we can vary A until we find the first set of interesting dynamics. So it turns out that if you continue to increase A further and further, there's multiple regimes of what appears to be chaotic motion and stable motion, chaotic motion, and it just goes on forever. So we're only looking at the first set of transitions that happen. Yeah.
Any more questions? If there's no further question, then we're going to ask member of committee stay and discuss the proposal. Thank you.